Okay, so here we're going to do a problem from section 3.6, which is our optimization section. Here's the scenario. We have a man building a pen alongside a river, so here's our river. We have a cost for the fencing. It's $2 per foot for the width, $3 per foot for the length, and we'll call this side the width, that side the length. Excuse me. And so we have a budget, so $900 is the max we can spend, and we're trying to maximize the area. So the equation that we're trying to maximize, the area, is the width times the length. But we have this constraint, and it has to do with the dollars, which refers really to our perimeter. So our perimeter formula would be 2 times the width plus the length. And it's not the amount of fence, but the cost. And so the cost, since the width is $2 a foot, it's 2 times 2W plus 3 times the length. And the cost being 900. So here's our cost equation. Well, I guess we could write it as an inequality because we don't have to spend up to that, but we're fine writing it as an equation. And so here, the equation that we're trying to maximize, the area, the problem is we have two variables. So we want this down to 1. So we'll use our cost equation. We will solve for one of these variables, substitute into our area formula, and then we'll have our area with respect to just one variable, and then we can find the max of that. So I think it's easiest here probably to solve for L, just because 900 divides by 3 very easily. So we have 900 minus 4W equals 3L, and when I divide everything by 3, we get 300 minus 4/3 W equals L. So we'll substitute that into our area equation. So instead of L, we have 300 minus 4/3 W, which gives us 300 W minus 4/3 W squared. And now the maximum we know can occur, and this is a closed interval. All right, the smallest we could have for W would be 0, right? We could go all the way down to 0. And if L was 0, we would have everything being with respect to W, so all the fencing there. So 900 divided by 4 would be 225. So there's our closed interval. And we know that a absolute max on a closed interval will occur either at an endpoint or at a critical number. So we know that if we have 0 for one of these sides, then we have no area. And if we max out at 225, the other side would be 0. So we also have 0 for an area. So now we know that the critical or the maximum must occur at a critical number. So we take the derivative, set that equal to 0. And when we solve this for W, we get W equals 112.5. And when we substitute W, or the 112.5, back into our cost equation, we can solve for the length. And so L is 150 feet. And the one thing we do want to do is we want to determine or make sure that we know that this is a maximum. And so we can either do a sign chart or number line for the first derivative and see that we change from positive to negative, or in most optimization problems, it's easier to do the second derivative test. And so the second derivative, if this is the first derivative, would be negative 8 thirds, which is a constant. Negative 8 thirds is less than 0. Therefore, we do have a relative max. And in this case, we know, because we've already tested our endpoints, that we know this is a absolute max. So the dimensions would be the width is 112.5 feet and the length is 150 feet.